Thank you very much for attending my talk, and thank you for the invitation to the organizer and for this pleasant conference. This time I would like to emphasize some problems related to nonlinear diffusion equation and nonlinear diffusion reaction equation, and we're introducing some solution and discussing some possible applications. In this case of the diffusion problems, we can propose analytical solution. The solutions are both numerical and analytical. The numerical one is an exact solution for the real problem, but the analytical one is a proposal based on a power law and a variational ansatz, allowing us to write an exact solution. These applications are very interesting and relevant. These results are possible to apply to in social science as well. These examples are chosen to illustrate some possible application. Among them, but they share a similar nonlinear diffusion behavior. For a long time, specialists have paid attention to distribution of facts and features of different properties of a wide nature of systems. Sorry. In the overview of the present talk, I give a motivation, the introduction, results. I introduce some concluding remarks. I'd like to emphasize that the Mozart music is related to statistics. For instance, a pioneer in the observation of distribution and the abnormal distribution, van der Kuit, a German physicist and musician, observed that there is at least an absent frequency in the entire musical work of Wolfgang Amadeus Mozart. There exists an almost forgotten frequency, and this is a problem that has various explanations in the literature. But at this point, if your question is what is the relationship between this problem with the rest of intention is only calling your attention about the relevance of the distributions. I'm not talking about this problem, but other problems related to this. We can emphasize the first case or the first possible application when we consider silicon conductivity. I like to remark that there are tendencies of conductivity that are not constant. Here, materials such semiconductor show an abnormal behavior because when we consider metals, the transport of transport is made by phonons. Laser and annealing experiment on planar surface layer of silicon and germanium, for example, using nanosecond synchrotron X-ray pulses as heat enters the sample, the temperature profile evolves more slowly than predicted by standard theories. consider a kind of a non-constant of our motivation, we can put this idea in the heat equation to get the temperature distribution taking a non-constant heat conductivity as, for example, in this figure. The red point show the possible behavior that we observe in experiment and that we find in the literature. In this case, we consider the temperature-dependent conductivity that we see in the figure is less than 0. Typically, alpha is around -1 for silicon conductivity in the range a range of the temperature. This simple observation leads to a nonlinear diffusion law because the parameter alpha is when the parameter alpha is equal to 0, the material can be a metal or a conductor, but the mean free path of carrier is too short and different from 0 for otherwise as expected, and the conduction is abnormal. Trying to construct an equation to solve the dynamic, we obtain merely the nonlinear version of the Fick law. This is the typical example of nonlinear diffusion. This behavior is pertinent because this equation is known as the diffusion equation for porous media, or simply porous media equation. In this picture, we see the tendency of the thermal conductivity in the red points. Fitting a power law, temperature dependent, we obtain alpha values less than 0, close to -1. In the second case, in this effort to make some physics applications of this kind of equations, we can emphasize, for instance, the diffusion in waveguide. We can exchange two types of ions, which starting from the Maxwell equation, it's possible to show that the concentration of base a nonlinear diffusion law. In particular, this equation is represented by a logarithmic term in the diffusion part of the diffusion equation. Then this is equivalent to the previous one. This part of the talk considers this problem possibly related to nonlinear optics for ionic diffusion in glasses. In ion exchange, two kinds of ion are in motion, the in-diffusing and the out-diffusing ion. Starting from Maxwell equation, we write a logarithmic diffusion equation like this remark, where the concentration obey finally a nonlinear diffusion equation. When we make a change of variable like this, we obtain a nonlinear diffusion law, and in particular a logarithmic diffusion law. However, when the parameter of D and D sub A and D sub B related to the parameter of this diffusion, the linear behavior is recovered. At this stage, we propose some analytical solution using two approximations, a particular power law and the traveling wave method. Okay, this part of the advance I try in the last part of the talk. Okay. Okay. I include a third problem, a third possible application related to population dynamics. In this case, we may interpret the distribution in terms of the population dynamics. To make an easy illustration of this case, we consider happy rabbit that finds some carrot to eat. They are so happy that invite other rabbits to share delicious food, then all together find new extra carrot. The problem can be studied through this equation like Lotka-Volterra equation or Verhulst equation, but I choose a third possible equation, and this is the Fisher-Kolmogorov equation that we call the extended Fisher-Kolmogorov equation. That it's very useful to discuss this kind of equation in biological system, but in physics system as well. We choose the Fisher and Kolmogorov perspective to write an equation that includes a diffusion term. This first term is the diffusion term and is nonlinear, and the reaction term in the last part of equation. These several challenges are related among them. Why are the question is why, but the diffusion term is very similar. When Q, in this case, tends to 2, this in the limit of this term, this term is a logarithmic equation like the system that we introduced previously. Well, mapping the population dynamic into social outbreak economic, this was inspired in the problem that in Chile occurs 2 years ago when a social outbreak was a problem that we need to solve. But the situation is that this kind of problem is possible to study about through this kind of equation. In the diffusion part of the equation, we consider typical nonlinear term, the two term equation. This equation is a kind of prey-predator model issues that we need to consume, for instance, okay? And the prey this is very interesting because all knowledge that we have in physics in the social outbreak economic problem into the relationship of each term of equation using social data. after writing or the extended Fisher-Kolmogorov equation, we are trying several parameters that that we find or that we need to solve the problem and relate well, in summary, we have three possible applications: solid-state physics, nonlinear optics, and dynamic population. The first two problems are possible to solve with the first part of the equation, but the dynamic population needs to the reaction term. But the system, and in this part of the problem, I need to emphasize that an unique answer solves the problem that we have here. Remembering the conductivity problem, in the literature, we find, for instance, a table and data that we find a problem in this situation, but we have with the answer that we put in the question, we can obtain two kind of solution. One of them is the diffusive distribution, and the traveling wave approximation solution is possible to obtain as well. And this is possible to put in for different times of the evolution. For instance, if we have a possible initial condition and we need to evolve for different times, we have how this super diffusive of problem with long tails are possible to obtain exactly from the equation and from the answer. In the other case, when we put as initial condition traveling wave like solutions, we that travel in the time, conserving its form. In all cases, in the first case, we conserve the. In the other case, we conserve the shape. In the other case, in the social case, we obtain two from the data, the initial condition for the diffusion reaction equation and the income employee to relate in the possible distribution that we need to put in the equation. Here, C is the data that we obtain for the income of employee, and W is the data for the per capita income. The other and the C in one case, the variation of the stationary solution, we can obtain some this I don't map with a certain problem that we obtain in our discussion. In the other case, this is the real behavior of the salaries, but these are the possible salary that we propose here. The best distribution is like this, okay? Like C3. The ideal distribution of salaries, okay? Very different in this is some possible detail of the calculation, but we are not put any detail here. But this is important because we have the perception dynamics. Perception is a variable, is a social variable because it's a subjective measure when we have a distribution like we have now. The perception of the income is like this, and when the population are decreases, and then can we have some social outbreak. In the other case, we can put distribution, an ideal distribution to obtain a perception, a different perception for the problem. In the conclusion, are relevant because we have some possible approximation to the complex system. The connection among several physics in every field. This is a possible to application of other problems that we obtain in general. Power law answer that like that we propose here can help to solve this kind of equation, nonlinear diffusion and nonlinear diffusion reaction equations, and support application in different perspectives, in different scenarios. The answer maximizes the general form of the entropy. This is a property, but this is not the center of the system, and this idea, but this is an antecedent. An additional solution using traveling wave approximation can be useful in nonlinear optics application. Okay, this is some contribution in this area. In the future, some challenges as well. Acknowledgement for recent collaborators and past collaborators as well. Okay, thank you very much.